Welcome back. So, the new thing today is that some things are gases, and we might still need to know how many moles of them we have. And there's a way to do that. It's called the ideal gas law, and usually when they write it out, they give it in this form, PV equals nRT. But if you're trying to find a number of moles from that, if you want to isolate N, then what you do is you divide both sides by RT, and then you get the form that we're going to be using for these few examples, which is that the number of moles of a gas equals its pressure times its volume divided by the ideal gas constant and also divided by its temperature. Now, the units for these gases are a little finicky. Pressure is measured typically in kilopascals, not just pascals. Volume is measured in liters. The ideal gas constant has compound units. It's liter kilopascals over moles and over Kelvin. And the temperature has to be in Kelvin. Celsius degrees are no good. So the two major traps are sometimes we give you the volume in something other than liters, like milliliters, and sometimes we give you a Celsius temperature that you have to tweak. If you have to do that, Celsius plus 273 or sometimes 273.15 equals Kelvin temperature. So that's an adjustment you may sometimes have to make. There are different versions of the ideal gas constant for people who work with other units, but we're always going to be using the same one. It's 8.314 liter kilopascals per mole Kelvin. And there are so many pressure units. There's kilopascals, there's millimeters of mercury, inches of water column, torr, atmospheres, bars. It's just dizzying. But for these, we're generally just going to stick with kilopascals. And just know that there are other units, and that if you ever see one of those, you may have to do some Googling to get those units whipped into shape. So, let's see what we can do with an example here. Another nice point about the ideal gas law, it works for every gas as long as the conditions are right. So when this says fluorine, we say, don't care. We don't have to do anything different for different gases with the ideal gas law, so that's a trouble saver. They tell us here they have a 400 liter volume. 400 liters. Pressure of 101 kilopascals. Temperature is in kelvins, so we don't have to fix anything. 286 Kelvin. And the ideal gas constant is always 8.314 liter kilopascals over molk. So our number of moles will be P V over R T. And out come the calculators. Now, a calculator mistake that some people make here. Here is something you must not do. 101 times 400 divided by 8.314 times 286. This, if you put it in a calculator, will not work because the calculator doesn't understand that both of these are in the denominator. If you give it this, that's like saying the 286 is up top, which is incorrect. The two ways you can fix it are you can bracket the denominator like this. That means divide by both of the following things. That will work. Or the way I do them fairly often, you can divide by both of these numbers. 101 times 400 divided by 8.314 and also divided by 286. This format will work. And if I do that now, 101 times 400 divided by 8.314 divided by 286, I get that the number of moles is almost exactly 17. It's 16.99, which would round to 17.0. So N for this is 17.0 moles of, okay, I guess I do care a little bit that it's fluorine, because when I get to the end and give my answer, I should say it's moles of fluorine. But it didn't affect the calculation in any way. All right, how will they try to mess with us in number 2? Temperature, 280 Kelvin. Kelvin is the right unit, so no need to tweak that. Pressure, 95 kilopascals. Volume, we want liters and they only gave us milliliters. So when you get this, you have to either shift the decimal 3 steps to the left or divide it by 1,000, because it takes 1,000 milliliters to make a liter. The actual volume is not 75, it's 0.075 liters. And the ideal gas constant is always the same number. I'll write it down just to remind you, 8.314. So our number of moles is P V over R T. .95 times 0.075 divided by 8.314, also divided by 280. Not much. Get 0.00306 moles of sulfur dioxide as SO2. Not too bad, I hope. One more. Okay, what have they given us here? Volume, 6.7 liters. So they didn't try the milliliter trick on us this time. Temperature, they tried the Celsius thing on us. Temperature is 18 degrees plus 273.15, gives us 291.15 is our Kelvin temperature. I know you see Celsius all the time, you get used to it, but it is no good for this kind of problem. This is what they call a relative temperature. This is an absolute temperature, Kelvin. That's what we must use. Pressure, they give kilopascals, which is fine. 99.5 kPa. And one last time, the ideal gas constant is 8.314 liter kilopascals per mole Kelvin. Tedious units to write out. Okay, so number of moles is P times V divided by R, also divided by T. And we pound the calculator one last time. 99.5 times 6.7, 8.314, and divided by 291.15. I get 0.275 moles of, what did they say, helium, which has the symbol just He. Not too bad. Definitely the least common mole formula that we will use, but you will see it from time to time, and it's nice to know you're ready.